In the previous video, we saw that covariance measures how two features move together, so let me remind you the formula of covariance. Covariance of x and y is equal to just an average of a centered x multiplied by a centered y. And if the central deviations usually have the same sign, covariance is positive. If they usually have opposite signs, covariance is negative. And it only measures the linear part of the relationship, so just the tendency to grow or to decay. And I said in previous videos that covariance depends on units. It has units of x and units of y. And that's a problem because if we, for example, change units of one feature, like change meters to centimeters, covariance changes, but the real relationship doesn't. So it's hard to interpret directly. And to remove the scale problem, we use correlation. Correlation formula looks like that. Correlation of x and y is equal to just covariance of x and y divided by standard deviations of each features. So let me remind you that variance of x also can be written like z is equal to an average of squared centered feature. Right, and the standard deviation of x can be written like z. It's just a square root of variance. So when we divide covariance by standard deviations, we have units of covariance, units x and units y from covariance, divided by units x from standard deviation of x, and units y of standard deviation of y. So they cancel each other out, and that's why correlation is unitless. And now let's see what this formula is really doing. So in covariance, we use centered values, right? So this part, when we subtract the mean, is centering operation. And in correlation, we go one step further. We divide each centered value by its standard deviation. So this operation called standardization, and obtained value is called standardized value, or z-score. So z-score of some feature x and observation I is equal to the value minus the mean, centering, and divided by standard deviation. So after this transformation, we have following. Mean is equal to 0 because we center the cloud of data. Variance of x of transformed features at x and is equal to standard deviation of this transformed feature and is equal to 1. So it means that if this new transformed value is equal to 3, then this value is 3 standard deviations above the mean. And if it's -3, then it's just 3 standard deviations below the mean. And now let's prove why the variance becomes 1. So we can just take a variance of this new transformed feature zx, and it's just an average, and then we substitute this equation. So it's just minus mean divided by the standard deviation and squared, right? So we can see that standard deviation is a constant, so we can move the constant outside, and when we do that, we move it first outside the bracket, so it becomes squared. And as a result, we have 1 divided by squared standard deviation of x, and then multiplied by an average of x minus mean squared. And we can see that this part is the same as variance of x, so we can substitute. And in result, we have 1. So this part, standard deviation of x squared, is also the variance of x, right? So we have variance of x and divided by variance of x, so it's equal to 1, right? So that score can be different, it can be like 2, -5, 10, and so on, but this standardization only makes the average squared deviation equal to 1, it doesn't bound individual values. And now we can rewrite the correlation formula as following, so we can just take the standard deviations and hide them inside covariance. It looks like that, so correlation of x and y is equal to an average of x centered divided by its standard deviation times y centered divided by each standard deviation, right? And we can see that this first part is exactly the standardized value of this observation, so it's that xi. So as you can see over here, it just subtracted mean and divided by standard deviation. And the same for this second term, so it's just standardized y observation, right? And that's why we can say that correlation is equal to an average of product of two standardized values, right? Like that. And we can replace this summation with dot product of two vectors if we know that zx, the dot product of zx and zy is equal to the first element of the first vector times the first element of the second vector plus the second element of first vector times second element of second vector, and so on. So it's exactly our multiplication, right? And as a result, we have z is equal to 1 and dot product of zx and zy, right? And this is important because it answers why we have correlation in the range from -1 to 1. So to understand that, we need to calculate the variance of the standardized zx, standardized x value. So it's just an average of zxi squared, right? Because it's already centered. And now we know that this dot product of two vectors in geometrical meaning is just a length of the first vector times the length of the second vector multiplied by the cosine of the angle between them. And we know that the length of the vector zx, for example, is just a square root of the sum of the squares of components. So it's just zx1 squared plus zx2 squared, and so on to the last zxn squared, right? And we know that the variance is equal to 1. So we can just take this part and multiply both sides by the n. So we have something like that. Zxi squared is equal to n, right? Because we just multiplied both sides by the n, and these terms cancel each other out. And now we can see that this part inside is equal to the, it is the same as the sum of zxy squared, right? So if we take square root from this part, from both sides, we have exactly the same equation of the length of the vector zx. So we can say that the length of the vector zx is equal to square root of the n, right? So it's equal to the square root of the number of elements in the vector. And same works for the vector zy, right? So this dot product of two vectors is equal to square root of n times square root of n and cosine theta, right? So it's just equal to n cosine theta. And when we put that to the formula of correlation, we have 1 divided by n times n cosine theta. So it's just equal to cosine theta. So correlation is just an angle between two vectors, right? And that's why correlation is just an alignment between two standardized feature patterns. And we know that cosine of theta lies from -1 to 1. That's why correlation is in the range from -1 to 1, right? So if correlation is equal to 1, it means that zx is equal to zy. So the standardized patterns are identical, and whenever x is like 2 standard deviations above its mean, y is also 2 standard deviations above its mean. And if correlation is -1, then zx is equal to -zy, right? So the standardized patterns are exact opposites. So whenever x is above its mean, y is below its mean by the same standardized amount. And if this correlation is equal to 0, it means that the standardized patterns have no clear linear alignment, right? So the dot product is equal to 0. So it's just like that. But it doesn't mean that there is no relationship at all, right? And if correlation value is between -1 and 1, like 0.8, it means that some strong positive linear tendency exists, but the points are not perfectly on the line. So the standardized patterns are similar but not identical. And the same if it's negative, so patterns similar but move in opposite directions, and points are not perfectly on the line. So correlation is calculated for two features across all observations, and each feature is standardized independently, but correlation compares them together observation by observation. And correlation, in the result, correlation, it's only one number. It summarizes a linear tendency between two features, but it doesn't show the full shape of the data. And here you can see for plots with almost the same correlation value, 0.8, but the structures are different. So in the first plot, you can see that the relationship is positive, so we have positive linear tendency, but the points are not perfectly on the same line, on one line. And in the second plot, the relationship is curved, so correlation is positive. It shows the tendency to grow, but it doesn't show the nonlinear shape. In the third plot, one outlier strongly affects the result, so we can see almost all the points are on the same line, but only one outlier strongly affects this correlation value, so it's not equal to 1. That's why we can conclude that correlation is sensitive to outliers, right? And on the last one, you can see that most points have almost the same x value on the vertical line, but one extreme point creates most of the positive relationship, right? That's why we should always look at some scatter plot to understand whether the relationship is actually linear, or the data is curved, or there are outliers, and so on. So to conclude, the correlation is useful because it gives us a quick, unitless summary of linear relationship. It helps to compare a relationship between different feature pairs, build the correlation matrix, and understand whether two variables tend to move together. But it doesn't fully describe non-linear relationship.